This video will cover Chapter 1 in our textbook. And Chapter 1 primarily covers problem-solving techniques. Specifically, at the beginning of the chapter, we start off with sequences. A sequence is just a list of values, so sequences. The best way to explain these is just to show you an example. Really what we're doing is looking for patterns. In this first example, we have 1, 4, 7, 10, ... So the pattern will continue. And we want to find the next term. Well, what we notice is that these terms are 3 units apart. So between 1 and 4, there's a distance of 3. 7 minus 4 is 3. 10 minus 4 is 3. So this next number must also be 3 apart, and so the next number is 13. So the next term is 13. And we could keep going, right? And then 3 more would be 16 and so on. But we want to also introduce some notation to denote a term. So each of these is a term. We use the letter A. And the subscript tells us which term we're on. We had the first, second, third, fourth. So we were on the 5th term. So A sub 5 is the next term, and A sub 5 is 13. If I go up and relabel my sequence, I have A sub 1, which is 1. A sub 2 is 4, and so on. A sub 3 is 7. A sub 4 is 10, ... So we could also ask for the term using that A notation, so A sub 5. Okay, next example. The next example has some fractions in it. The first term is 1/2, negative 1/3, 1/4, negative 1/5, ... Again, we want to find the next term. But the pattern's different this time. Or A sub, let's see, first, second, third, fourth. We're looking for A sub 5 again. So I'm really looking for a pattern. What I'm doing is using inductive reasoning to make my best guess at the next term. I don't really know what the next term is. I don't know exactly what the person had in mind when they wrote this, but I have a pretty good idea. That's what inductive reasoning is. I'm not using any rules or specific formulas. I'm just looking for a pattern. So I notice that the 1 stays in the numerator. So I know that the numerator is going to be a 1. I alternate positive, negative, so I must have a positive for my term. And my denominators are counting numbers starting with 2. 2, 3, 4, 5. So the next one must be 6. Again, I used what's called inductive reasoning. There are no guarantees with inductive reasoning. Just means I'm making my best guess at the next number. Okay, so for example, let's say that we had 1, 2, 3, and we wanted to guess the next number. So for this one, we're looking for, let's see, first, second, third, the 4th term, which would be A sub 4. And I think the obvious choice here would be that we just keep going up in the counting numbers, 1, 2, 3, so that one would be 4. But what if we noticed a different pattern? And a different pattern might be, for A sub 4, that to get to the 3, we added the 2 plus the 1. So the 3 is 1 plus 2. Which means if I want to get to the next number, I would add, let's see, 3 was the previous 2 numbers. So this one would be the previous 3 and 2. So this one would be 3 plus 2, or 5. So we might recognize a different pattern, especially with so few numbers given. And we could also make a conjecture that the 4th term in the sequence is 5. I think most people would guess 4, but this would be another reasonable choice for the next number. So again, inductive reasoning, there are no guarantees. We're just looking for patterns. Next example. So in this one, we have another sequence of numbers, 1, 11, 35, 79, 149, 251, ... And we're going to look for a pattern. I don't see anything obvious. I'm not adding 3 each time. I'm not changing fractions like I did before. So I'm going to look at successive differences. So I'm looking at the differences between each of my terms, like I had done before. I get 10 here. The difference between the next 2 terms is 24. And let's see, that would be 44. 149 minus 79 is 70. And 251 minus 149 is 102. So I'm going to do successive, can I fit it in there? Differences. And these are successive differences because I still don't see my pattern. I need to do the differences again. This is the successive part. So now I look at the differences between these numbers, these differences. 24 minus 10 is 14. 44 minus 24 is 20. 70 minus 44 is 26. And then 102 minus 70 is 32. Okay, do you see a pattern now? If you notice that each of the numbers go up by 6, you're right. And I can prove that with one more level of my differences. 14 and 20, their difference is 6. 26 minus 20 is 6. 32 minus 26 is 6. So now I need to work my way back up. Let me get my yellow pen. Work my way back up to the next term. Okay, so I need a 6 from 32 to the next number. 32 plus 6 is 38. To get to this number here, which was my first level of differences, I need 102 plus 38, which is going to be 140. So to get from 251 to the next number, I need to add 140, which is 391. So 391. Let's label that. This is first, second, third, fourth, fifth, sixth, seventh term. So we just found the next term, which is the seventh term. So a sub 7 is 391. Again, this is another form of inductive reasoning because we're using differences. Even though it feels like we're using a formula, we're really just looking for a pattern using those differences. The next topic is sums. So now we're going to take some of these lists of numbers and start adding them up. So B, sums. Another term for these is a series. So a series is when you add the terms of a sequence. And you can just use sums. That works. Okay, number 1. Let's add up some counting numbers. 1 plus 2 plus 3 plus 4 plus, let's go all the way to 100, plus 99 plus 100. This would take me a long time. Even if I were to type all of these into my calculator and let the calculator do the work, this would still take me a long time to come up with a number. So what we do is we look for the pattern, and this pattern is Gauss's pattern. He was a mathematician, and the story goes that Gauss was a young boy, and his teacher in elementary school wanted something to keep the children busy, so she had them add the numbers 1 through 100, and Gauss was done really quickly. And what he did, instead of just adding 1 plus 2 is 3, plus 3 is 6, and so on and so forth, he instead looked for a pattern. So here's what Gauss did. So this is Gauss's method. Is there an apostrophe S or an apostrophe? I don't know. Anyway, this is Gauss's method. So instead of just going by brute force, which is just adding them as given, instead Gauss noticed this pattern. If you add 1 and 100, so 1 plus 100, you get 101. When you add the next two terms in the middle, which would be 2 plus 99, you get 101 again. So 2 plus 99, you get another 101. The next one would be 3 plus 108, or sorry, 3 plus 98, 98, which would be another 101, and so on. 4 plus 97 is another 101, and we would be able to pair off these numbers in the sum until we get all the way down to 50 plus 51. Those would be the last two numbers. Those are the middlemost numbers, which gives us another 101. So what we end up with are 50 sums. So we have 50 sums that add to 101. So when we're putting these sums together, to come up with this sum, we get 50 101s. And if I multiply 50 times 101, we get 5,050. That would be our answer. So we're using a pattern to come up with the answer to this sum. Let's do another one that's not up to 100. Let's do, still adding counting numbers, so we'll do 1 plus 2 plus 3 plus, let's go up to 200 this time. So 199 plus 200. So using the method of Gauss, we do the same pairing. We start with 1 plus 200. 1 plus 200 is 201. 2 plus 199 is going to be another 201. 3 plus 198 is another 201. And we're going to be able to go all the way down to the numbers in the middle of this list here, which will be 100 and 101. Those are the ones next to each other. 100 plus 101, which is the last pair, the middlemost pair for 201. So now what we have are 1, 2, 3, all the way to 100. So we have 100 sums of 201. So to come up with our sum, we multiply 100 times 201, and we get 20,100. So that would be the answer to the sum. So for that method of Gauss, you're going to pair them up, outermost, and then the next pair, and then the next pair. Figure out what that sum is and how many of those you have. There's a formula, but I think if you've got this method down, you won't need to memorize that formula. Another sort of famous sequence of numbers to add are the odds. So 3. Let's add the odds. 1 plus 3 plus 5 plus 7 plus ... We're not going to add all of them. This ... really means that there's infinitely many to add. But what I want to do is to do some partial sums so we can see a pattern. So for a partial sum, I'm going to use a capital S to denote the sum, and S sub 1 would be the sum of the first number. That's just 1. S sub 2 would be the sum of the first two numbers, 1 plus 3. So 1 plus 3, which is equal to 4. S sub 3, I add the first three numbers, 1 plus 3 plus 5. That's 4 plus 5, which is 9. Do you see something in common with those numbers? S sub 4, that would be 9. I'm just going to take the last sum, plus the next number, which is 7, which is 16. I'll do one more. S sub 5 is going to be the first four numbers, which added to 16, plus the next odd. I don't have it listed up here, but that would be 9, which is 25. Okay, what do 1, 4, 9, 16, and 25 all have in common? Do you know? These are all perfect squares. Okay, where's my orange pen? 1 is 1 squared. 4 is 2 squared. 9 is 3 squared. And notice what sum we're on. When I add the first 3 odd numbers, I get 3 squared. When I add the first 4 odd numbers, I get 4 squared. I add the first 5 odd numbers, I get 5 squared. So I can come up with my sum if I know how many odd numbers I'm adding. Okay, so for example, let's say that we've got 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15. So to come up with my sum, I just need to figure out how many odd numbers I have. 1, 2, 3, 4, 5, 6, 7, 8. So my sum must be 8 squared, which is 64. But what if we add more odd numbers than just those? Let's say that we do 1 plus 3 plus 5 plus ... all the way up to 57. Well, I don't want to write all of those out. But instead, I can think of it this way. I have all of the odd numbers. So I'm taking all the odds between 1 and 57. Okay, well, we got that, which is half of the counting numbers between 1 and counting numbers. I need to go up to 58 to get it in between 1 and 58. So half of the counting numbers between 1 and 58. So really what I'm doing is I'm going from 1 to 58, but I'm skipping the evens. So I'm going to take half the numbers between 1 and 58. So to figure out what that is, that would be 58 numbers, but I want half of them, so that would be 29. So I have 29 odds. So the answer then would be 29 squared, whatever that is. Well, let's check this. Let's check going up one number and then dividing it by 2 so that we've got half the numbers in between. And let's check that with one of the examples we just did, like this one up here. So I've got 1 through 15. We could count that up, and there were 8 of those. So really what I'm doing is I'm taking half the numbers between counting numbers. I'm just abbreviating it. Half the numbers in between 1 and 16. Or there are 16 of those divided by 2, and I have 8 odds. And that's exactly what we counted here, 8 odds. So to figure out how many odds, go up to the next even number, divide it by 2. That tells you how many odd numbers you're adding, and then square it. So that's a really nice pattern for adding up the odds. The last topic that we're going to cover is some additional problem-solving techniques. So far, the problem-solving techniques that we've seen are inductive reasoning using patterns. We also saw Gauss's method, and then this nice pattern that we saw for adding the odds. C, problem-solving strategies. I'm going to just jot a few things down here. I'm sure these are things that you have thought of and probably used in some different math classes. So some good problem-solving strategies would be draw a picture, look for patterns, just like we did here up above, look for patterns, maybe solve a simpler problem. So if the problem's really complicated, maybe you can pull a pattern out of a similar problem that's just a little simpler. Let's see, draw a picture, do patterns, and then you can also just guess, which sounds a little more formal if you call that trial and error. Trial and error. Okay, so there's a lot of different problems that we're going to find in, I think this is section 1.3, a ton of different kinds. I'm going to do just a few to show you what some of the techniques are. So here's our first example. How many squares are in the figure? Okay, so let me draw the figure. It is a square, and the square is divided up into 3 columns and 3 rows. So I could just start guessing. A square is any figure that has the same length and width. So I could just start guessing and listing them out, but instead I'm going to organize myself. I notice that I've got 3 different sizes. There's a 1 by 1. So this right here would be a 1 by 1. So we have 1 by 1 squares. I'm going to count those up, and I will do that in just a second here. I've got a 2 by 2. The 2 by 2 squares look like this. And then, of course, I've got that largest 3 by 3. 3 by 3. And I don't have any other sizes. So rather than just counting and hoping I get them all right, I'm going to organize myself and count my squares by size. Okay, how many 1 by 1s? Well, there's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So for the 1 by 1s, there are 9 of them. For the 2 by 2s, I'm just going to start here in this corner. So I've got 1 here. And if I scoot over, I've got another one here. So 1, 2. So I've got 2 across the top. And then down at the bottom, if I shift this all down, I've got 2 more. 3 and 4. So I've got 4 2 by 2s. And then the 3 by 3 is the largest one. There's only 1 of those. That's the outermost square, which is this guy. 1. So pretty quickly I came up with my answer. I just need to add these together. 9 plus 1 is 10, plus 4 is 14. So we have 14 squares. So what I did here is I didn't really draw a picture. I'm going to say or chart. Kind of made a chart, didn't I? 1 by 1, 2 by 2, 3 by 3 to organize myself. Here's another type of problem that you might see in this section. There's a lot of questions about a digit of a number with a really high power. What is the units digit of 3 to the 324th? Well, the very first thing that I would do is to pick up my calculator and ask my calculator, what is 3 to the 324th power? And then I hit enter. Can you see what it says? It says error overflow. It's too big. It's too big of a number. Even my $120 calculator here won't calculate that for me. So instead, I go back to the drawing board and I start looking for a pattern. So I can do 3 to the first. So this is really a combination of these two. I'm going to start solving simpler problems, ones that I can find the units digit for. And as I'm doing that, I'm going to look for a pattern. 3 to the first is 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th power, that would be 9 times 9, that's 81. 3 to the 5th power is 81 times 3. So 3 to the 5th power is 243. Oh, now I'm seeing a pattern. There's that 3 again. Let's see. So 3 to the 6th power. So 3 to the 6th power, I'm using my calculator over here, is 729. Let's take a look. 3971. 39. I'll bet 3 to the 7th ends in, let's see, 39 ends in a 7. So 3 to the 7th, which my calculator can still handle, is 2187. Okay, so far so good. 3971. 397, so I'll bet 3 to the 8th power ends in a 1. So let's see, 3 to the 8th power, and it does, 6561. 6561. So my pattern then are in groups of 4. 3 to the 1 through 4 power, 3971. 3 to the 5th, 6th, 7th, and 8th, 3561. So that ends in a 1. So 3 to the 9th must end in a 3. 3 to the 10th must end in a 9. 3 to the 11th must end in a 7. And 3 to the 12th must end in a 1. Okay, so I see the pattern, but I've got a long ways to go before I get to 324. Well, really what I notice is that I'm taking my powers, 1, 2, 3, 4, and I'm grouping them into 4s. So really now the question becomes, how many groups of 4 go into the power 324? Here's something else that you can notice. Take a look at what happens when I land on the 1 here. 3 to the 4th, 3 to the 8th, 3 to the 12th. All of these powers are multiples of 4. 3 to the 4th, 3 to the 8, which is 4 times 2, 3 to the 12th, which is 4 times 3. And when we get to the next number that ends in 1, it's going to be 3 to the 16th power, because that's going to be 4 more. So as I'm building this pattern, I really want to know, does 4 divide into 324? So I really want to figure out how many groups of 4 I can get out of here and if I have any remainders. So I'm going to do 4 into 324. Well, actually, I'm going to let I can do it by hand, right? 4 into 32 goes 8 times. 32. And then I bring the 4 down, so it goes in 81 with no remainder. Which means that 324 is a multiple of 4. It's one of these guys, 324 is. So if I were to put in my list, in my pattern, 3 to the 324th, it would be one of the ones that I've circled there because it's a multiple of 4, and I know that those are then going to end in 1. So whatever that huge number is, the units digit is 1. There's lots of different kinds of problems that you're going to come into contact with when you're working through this chapter, but kind of keep these strategies in mind. We're looking for patterns, which is inductive reasoning. We're looking for organizing our work, like we did here. And then we also have a few formulas that we used for Gauss's method of adding the counting numbers and also for adding the odds.